examples will be on duality, and the next two solved examples will be on finding the optimal point, x star. Okay, so we'll look at duality first. Okay, just a quick review. Optimality conditions are this is the constraint optimization problem, and this is the Lagrangian. So we have the inequality constraints, the equality constraints, and then we form the Lagrangian, and lambda must be greater than or equal to 0, and that's part of the first order condition. So these are the set of four necessary conditions for optimality. Primal feasibility, of course, these two must be satisfied at x star, the optimal point, and dual feasibility, lambda star, must be greater than or equal to 0. Complementary slackness and stationary are ones that we will be focusing on while solving problems, and you'll see that there's an interesting way to handle this that you'll see in example 5. Okay, and so these are the necessary conditions for optimality. And second order conditions are there. We will probably not look at second order conditions here, but we could still check. Okay, so this is the second order condition for optimality. And now duality theory. So this is the primal problem. We take the Lagrangian and maximize with respect to the dual variables, right? And then minimum with respect to x of this is the primal function. Minimum of this with respect to x is x star. Okay, and this is theta p of x, and this is the when we do the infimum, we get theta p star. And then the dual, what you do is take the infimum with respect to x of the Lagrangian, and you get a function that's only in terms of the dual variables, lambda and mu, and maximize that with respect to the lambda and mu, you get lambda star, mu star. So this is theta d lambda mu, and this is the maximum of theta d lambda mu, and the maximum of theta d lambda mu will always lie below the minimum of this theta p. Anyway, so and strong duality will be, it's quite easy to satisfy strong duality, but in that case, this red curve, which is theta d, will touch the primal theta. Okay, so now let's begin with example 1. Okay, so minimize this objective function f of x1, x2 equals 1 over 1 plus x1 plus 2, 1 over 2 plus x2, subject to x1 plus x2 equals 3. Now, using just your knowledge of calculus and common sense, you can always address this problem, right? But you won't be able to find the duals. And of course, we can address it in that way. We can simply replace x2 equals 3 minus x1, and then this whole function will be expressed in terms of x1 only, differentiate it, and get the solution. But we will use the former method of solving it, so that we also get to look at the dual. And actually, in this case, we'll just find the dual. We don't have to solve it here. Okay, using the dual to solve it, you need a numerical method. Okay, so this is our primal problem. Lagrangian is this. F of x1, x2 is this, and plus we have a mu equality constraint, mu. That's the convention that I usually follow. Lambda for inequality constraints, mu for equality constraints. So mu x1 plus x2 2 minus 3, and so this is the Lagrangian. What I've done here is, luckily, the terms containing x1 and the terms containing x2 can be separated out. So this is my Lagrangian. Let's take this expression to the next slide. So this is what we have. This is our Lagrangian. Now, in order to find the dual, what do we have to do? Eliminate what? X1, right? We have to minimize with respect to x1. Okay, so theta d mu is minimum with respect to x1 and x2 of this Lagrangian. Now, it's a good thing that the terms containing x1 and the terms containing x2 we were able to separate. Okay, so this set of two terms, this contains only x1. So we can minimize this with respect to x1 separately, and likewise, these two terms here we can minimize with respect to x2 separately. And this negative 3 mu arises from x1 plus x2 equals 3, and so this is independent of x. So this is the expression that we have, and so now let's go to the next slide. So here we are. This is the expression that we just obtained. Let's attempt to minimize this one. So taking the derivative and letting it equal to 0, what do we get? So negative 1 over 1 plus x1 square plus mu equals 0, whence x1 equals, solving this, we get x1 equals negative 1 plus minus square root of mu. We have two solutions because we have a quadratic here. Okay, and then replacing x1 here and simplifying further, actually it's quite easy to do the simplification because you see you have 1 plus x1 here, and here you have x1 equals negative 1 plus. So 1 plus x1 equals plus minus square root of mu, right? So it's this is 1 square root of 1 over plus minus square root of mu. That's it. Okay, and so we get this as our solution. So this is the minimum of the first minimization. Okay, and we'll remember this. These two we'll keep aside. We'll use these two expressions later. And then what we do is, in exactly the same manner, we try to minimize this. And taking the derivative and equating to 0, we get this here, and solving x2 equals negative 2 plus minus square root of mu. And as before, you see you have 2 plus x2 here, and here you have x2 equals negative 2, right? So when you replace x2 with this value here, it'll be very easy to simplify. And so you get this expression here. So this here simplifies to this. And you can indeed verify that these are minima with respect to this one with respect to x2 here, and the previous one, this one with respect to x1 here by taking the second derivatives. Okay, so this is where we are. This is what we got for the second term. And we'll remember this and this, store it aside for later use. Okay, so this is what we end up with. Theta d is now purely in terms of mu. Okay, how did we arrive at that? Because we saw that this minimization yielded these two terms, and then this second minimization yielded these two terms. Okay, so that's what we are at, and we also have these two expressions. So Simplifying this, we get this. Okay, so now one thing you will observe, you have square root of mu. Now, typically mu can have any value. It's unrestricted because it corresponds to a equality constraint. Correct? So mu should be able to acquire any value between negative infinity and infinity. However, in this case, you specifically see that if mu were to be negative, then you would get square root of a negative quantity here. So we're sticking to real variables. Okay. So we must have mu greater than or equal to 0. Furthermore, if mu were equal to 0, then you can see that this would be 1 over 0, this would be 1 over 0. Correct? So again, we must disallow these cases where mu equals 0. You want to minimize, correct? But you'd get infinity here and here if the denominators are equal to 0. Okay, hence mu must be strictly greater than 0. Now, how to address a strictly greater than 0, I will tell you later in a couple of slides. Okay, because we are used to something being greater than equal to 0 or less than equal to 0, right? The way we formulate a problem, optimization problem. Okay. So this is where we are at. Okay, now mu must be greater than 0, strictly greater than 0. Now we have to maximize this because this is theta d, right? You see, we have different possible cases for theta d. If you take plus here, then you plug in a plus here. If you take minus here, then this would be a -2. If you take plus here. If you take minus here for x2, then this again would be negative. So now we want to maximize with respect to mu. Correct? So what should the plus and minus here, the plus and minus be? Mu is greater than 0. So these two terms, ignore the plus minus signs, these two terms are all positive, right? When we want to maximize, why do we need the negatives? We can discard the negative values, right? Because this admits two possible solutions. This also admits two solutions, right? But we don't want the negatives here because we want to maximize the function, right? So we just ignore the negatives here. Okay, and therefore, by implication, so this is replaced with strict pluses. These two we have to therefore take the pluses. Okay, so this is what we are at. This is the the dual objective function, or the dual function, and this is a constraint in the dual. It's a common sense constraint in the dual. Okay, so this is what we are at, and notice that I've replaced the strictly greater than with greater than equal to here. So this is the dual problem. This was the original primal problem. You can further simplify this. Maybe you can let zeta square equals mu. Okay, so this will be 1 over zeta. This will be twice 1 over zeta cubed, and this would be zeta square. So this would be a polynomial with respect to zeta, and no square roots involved, no over 2. And so mu equals zeta square if you allow, then you don't even need this one, right? It will automatically, mu will automatically be positive. It's zeta square. And so you can then solve with respect to zeta. Did you understand what I said? Yeah.
Yeah, so isn't it mu raised to 3 by 2?
Oh, what you're saying is this one, mu plus 3 by 2. Possibly, let's see, there is a typo here.
But I guess still all those conditions will hold.
Yeah. It could be a typo. Let's check. So this would be x2 equals, so we're looking at this one, right? So this would be 1 over square root of mu. Plus minus 1 over square root of mu, this term. Mu x2 would be, yes. So mu x2 will be negative twice mu plus minus, yeah, you are right. Square root of mu times mu plus 3 over 2. I'm so sorry. So this is a plus here. And I guess it's the same thing with the previous one. Thank you so much for catching this mistake. So this one, I guess, should also be a plus. There's a plus sign here instead of a negative sign. And likewise, there's a plus sign here. And therefore, so we were here. So this would be plus. But the conditions would absolutely be the same. All you have to do is make those changes. Negatives become plus in here. Okay, now how do you solve this problem? Address this problem of mu being strictly greater than 0, which is what we want. Mu equals 0 is not admissible, right? Because otherwise, both the terms would become infinity. Now, the way to address it is, well, you have to use less than equal or greater than equal constraints when you are formulating a constraint optimization problem. Okay, and in fmincon and MATLAB, that's the way, that's what's allowed. Where, equal being something greater than equal, if it's strictly equal, then that constraint is active, otherwise it's inactive. Okay, so we don't handle situations like this, mu being strictly greater than 0. So what we have to do under these circumstances, in general, when you have a problem like this, where you need something to be strictly greater than 0, algebraically, you can write mu plus lambda is greater than equal, not lambda, mu plus epsilon, where epsilon is an infinitesimal, is greater than equal to 0. That's one way to handle it. Otherwise, when you numerically solve it or algebraically solve it, you get an expression. Discard wherever mu equals 0. Reject anything you get with mu equals 0. Okay, so that's how you have to handle this. Okay, now when we solve this dual problem, by the way, is a little simpler than the primal. Okay, to solve. Now, this, to begin with, it has only a single variable instead of 2 variables, right? Well, of course, x1 plus x2 equals 3 is hardly 2 variables, but still. Now, what was I saying? Yeah. You must have the equality here, because when we are solving the dual problem, dual constraint optimization problem, then mu equals 0 corresponds to this constraint being active, and mu greater than 0 corresponds to this constraint being inactive. Okay, so you have to have greater than or less than equal to. Anyways, any other questions here? Thank you so much for catching that mistake.
I had a doubt whether this will change. That's why I just.
Okay, so this is example 1.
What kind of issues actually raised with the active state? if we have u is equal to 0 and if it's an active state,
active constraint,
so what kinds of issues can be arise?
well, what kind of problems would arise if this constraint were active?
Yes.
If mu were active, we set mu to 0. What happens to x1 here?
One thing is it become infinite.
Infinite. So x1 and x2 become infinite. We are trying to minimize this function, correct? So what we would land up with here is a situation where the function is infinite. Obviously, it's not the minimum. Does that answer your question?
That is actually related to the problem, but is it always a problem to have an active constraint?
You must have. No. Well, it depends on the problem, what the solution is. Okay, and we will be looking at the example 5. I'll have all possible cases when we'll try to solve a constraint optimization problem, and we'll look at all possible cases where a constraint is active and it's inactive. Okay, and in this case, in this problem, here, the constraint, an equality constraint, is always active. Correct? Because, excuse me, I'll turn it off. I never expect any calls here, and this was a scan. Sorry about that. Power off. Okay. Okay, so any other questions? Okay. Now, this was with an equality constraint. Now, the next example that we look at is again how to construct the dual, theta d, but we will have an inequality constraint now. Okay, so this is a very simple problem. This is inequality constraint prime. Minimize f of x equals x squared plus 1, subject to x squared minus 6x plus 8 is less than equal to 0. This is our primal problem. This should be inequality constraint primal. And then this is the Lagrangian objective function. And observe, this is a minimization. Why I put a negative here? Don't remember. Maybe it was should have been a maximization. I don't remember. But anyway, so for some reason I put a negative sign. For this problem, I typically use a positive sign here. Anyway, so, and lambda is greater than or equal to 0. It should have been a maximization or something, I think. But we'll see. So this is, in which case it would be justified to put a negative here, or this would have been a plus, greater than or equal to constraint. I don't remember. Okay. Excuse me. So this is the Lagrangian. And so what I do is I write it in terms of the quadratic. This is the quadratic term, x squared. Oh, this is a typo. That explains it. This negative should be a positive. Nothing wrong here. It's a minor typo here. This should be a positive. Okay, so this is a positive. And so this is what we have. So this is plus and this is negative. So we have minus 6 lambda x, and then we have, this is positive, right? So plus 8 lambda plus 1. Okay, so this should be a positive here. So this is the Lagrangian. Let's remember it. And now, this is the Lagrangian again. And then theta d is to minimize this with respect to x. It's a simple quadratic. Correct? And so, derivative of this has to be equal to 0. Derivative of this is equal to this, which is equal to 0. This derivative equals this, which is equal to 0. So x equals 3 lambda over 1 plus lambda. Sorry about these. Derivative equals this. That's what I should have. Oh. It's hard to do all these edits. Okay, so this is what we have. Derivative of theta d lambda equals this, whence we get x equals 3 lambda over 1 plus lambda. So theta d lambda equals, replacing x with 3 lambda plus 1 plus lambda, we get theta d lambda equals this. Okay. So this is x in terms of lambda. We'll use this later, and this is theta d. Any numerical mistakes? Okay, so this is then the dual problem. This is theta d lambda, and lambda we know is always greater than or equal to 0. So this is the dual problem, maximization. And this is the corresponding primal. Okay. Now, one issue is the dual of the dual equal to the primal. Okay, now that's a question that might arise in your minds. The answer is not necessarily. There's a special class of problems for which the dual of the dual is the primal, and you'll see that in linear programming. Those are called like self-duals. And we have, so this is the dual problem. If you solve the dual problem instead of a primal, you should use this one. Now, which looks more complicated, the primal or the dual? Well, it depends, right? Well, here you have a more, complicated constraint. Here, all you have to look for is lambda greater than or equal to 0 and solve this. Okay, so example 3. Now, this example I took from a textbook. The other ones I just devised. This one I took from a textbook, but it's a very interesting approach. Okay, it's simple, but it's quite interesting, and you'll see. That's why I borrowed it from. You might have heard of this textbook. It's probably the standard textbooks on convex optimization. Boyd and Vandenberghe. And so minimize f of x equals x transpose qx, simply a quadratic, subject to xi squared minus 1 equals 0. Equality constraint. Now, this is actually an example of a discrete or a binary quadratic problem, optimization problem. because the only solutions are for each xi to be either +1 or -1. Okay. It's just two-valued, so it's very specific. It's binary, but in general, you have discrete optimization problems. So you have to find all combinations of +1s and -1s that would minimize x transpose qx. Okay. Now, let's see how to construct the dual of this. It might not turn out to be something simpler, but at least we'll see what happens. Okay, how to deal with unusual situations. Okay, so this is the primal problem. Construct the Lagrangian. I have this xi squared minus 1 here, xi squared minus 1 equals 0, and so I have mu i's as the equality constraint Lagrangian. So this is mu I, okay, and we have n of those. So theta d mu equals infimum of this Lagrangian, correct? Store this aside, and so this is what we have, theta d. Okay, which is equal to, now this one, you can simplify it from your knowledge of matrix methods. This would be x transpose q plus diag mu I of x. This is also a quadratic term, right? Mu I x square, right? So this is what you get. Diag mu I is a diagonal matrix with mu1, mu2, mu3, mu4, and so on as the diagonal elements. So this and this, all the summation of mu I with a -1 here becomes mu transpose 1 or 1 transpose mu, either way, same thing. Okay. Now what happens? And x is otherwise, you don't have any other restrictions on x here. Okay, now when you're doing the theta d, again, remember I told you a long time ago that we are not considering the constraints. When we are trying to get this theta d or theta p, we are simply trying to look at the infimum. And somehow the constraints will take care of themselves. Okay, so here, this is where we are at. What would be the infimum? X transpose qx or x transpose q plus diag mu I of x. Okay, now if this has a negative eigenvalue, okay, then what will happen? For some x transpose qx or q plus diag mu I x, you will get it can become negative, right? In which case you can set it to some value, x to some value such that this becomes negative infinite. Correct? And so, only when this is positive definite or positive semi-definite, q plus diag mu I is positive semi-definite. Okay, then x transpose of this matrix q plus diag mu I times x, this quadratic will never be negative. It'll always be non-negative, 0 or positive. Correct? And so we will only consider the case where, so this is what happens. If this matrix is not positive semi-definite, then the infimum is negative infinity. Right? But only when this matrix here is positive semi-definite, then what we can do is we can adjust x to make this equal to 0. It's bounded at 0, right? It's like a upturned parabola, cup shape. in multiple dimensions. Okay, otherwise it will be maybe cup-shaped in one axis, but another axis it will be inverted cup-shape. Okay, so only when this is SPD, SPSD, positive semi-definite, then how do we minimize? By picking the value of x, which makes it 0, this term 0. Okay, and so in that case, we are left with negative mu transpose 1. Okay, now, so this is what we have. We want to maximize now with respect to mu, right? Now, when we maximize with respect to mu, okay, so this is theta d effectively. Now, when we are maximizing with respect to mu, we can reject this second case of negative infinity because we're trying to maximize, right? So we will only try to find mu's such that q plus this is greater than equal to 0. Okay, and this constraint is actually not that hard to enumerate because if you look at all the if you have all the eigenvalues of q, right, the eigenvalues of q plus diag mu I will be eigenvalues of q plus mu I. Okay, so those should be greater than equal to 0. So this can be reduced to a set of greater than equal to constraints. Do you see what I'm talking about? So this is what we have. Now, so negative infinite we discard and we constrain mu's so that this holds and find mu within this bound. That would do what? That would maximize this because we'll be maximizing with respect to mu. So this is what we have. Maximize negative mu transpose 1 subject to q plus diag mu I is greater than is positive semi-definite. This is the primal problem and this is the dual. Okay? And this, by the way, is for large values of q, okay, or for large dimensions, this is prohibitively expensive. The primal problem. Because we have to consider if this is, if we have n dimensions, right? This lowercase n dimensions. So we have to consider 2 to the power of n number of possibilities. Imagine when n is 25 or 30 or something. It's just mind-blowing, right? There's no way you can solve so much. Okay. So this is the primal and this is the dual.
So this diagonal of u of I means the u of I at the diagonal?
Yeah.
And for this constraint, both q and the diagonal of ui both need to be positive?
No, there's some.
There's some. But if q is positive definite and if diagonal of ui is positive definite, then the sum will be positive definite, isn't it? Is there a case if q is positive definite and one is not positive definite, but the sum is also positive?
Yes, yes.
Okay.
It's just like x plus y greater than 0, greater than equal to 0. Doesn't mean that x is greater than equal to 0 and y is greater than equal to 0. Right? Okay.
The other case will hold, right? If individual results are greater than 0 than up to 3.
Yes, if Q is positive semi-definite, then and lambda, what we can do is if Q is positive semi-definite already, then we can simplify this by we can let all the mu's, excuse me, greater than equal to 0. And then solve it. It becomes a lot easier, right? Okay. So this is example 3. And so with this, you have seen how to, with a couple of examples, you have seen how to obtain the dual. Okay. Now let's do 2 problems where we actually find the numerical value of the constraint optimization problem. Primal or dual, we don't need to convert it to the dual, but what we need to do is satisfy all the necessary conditions. So the first one is pretty easy. Okay, actually, let me show you the figure. See, what I thought of this problem. This is a cross-section of a loaf of bread. Okay, and so assuming the baker has a fixed amount of dough, okay, and he can prepare the bread in any form, but the cross-section, if the length is fixed, then the cross-section, the area would also be fixed because he has only exactly so much amount of bread, okay. And so what he's trying to do is maximize the or reduce the total baking time or something, and he can do that by, I guess indirectly, by maximizing the surface area or the perimeter of the cross-section. So this is the perimeter of the cross-section. This is the breadth, this is the height, and this upper half, this is kind of how a bread is shaped. This is a semicircle. It's a half circle, okay? So this area is BH. The radius of this circle is b over 2, and so half of the area of a circle will be pi over 8b square. And the perimeter of this perimeter will be pi over 2b of the half circle, and this will be h plus b plus h, so b plus 2h. So this is the perimeter that the baker wants to maximize. And this is subject to this constraint. So this is a very simple example of a practical problem with equality constraints. Now, you might notice that there are 2 hidden inequality constraints. B and H have to be strictly positive, greater than or equal to 0, let's say. Okay, now, either, there are 2 ways to approach this. Either I can explicitly include the inequality constraint. H is greater than or equal to 0, B is greater than or equal to 0. In which case, I will get how many dual variables? I'll get one mu variable for this, and for H greater than 0, I'll get a lambda 1. For B greater than 0, I'll get a lambda 2. So I have a 5 variable problem, B, H, and mu and lambda 1, lambda 2. Another riskier, maybe, approach is to assume that, okay, what I'll get is H equals 0 and B equals 0, you won't get because the, look at what will happen to this, right? You can assume that, okay, this is a practical problem. Definitely the solution would be H is greater than 0 and B is greater than 0. Okay. If they're strictly H and B are positive, not zeros, then the constraints are inactive. Lambda 1, lambda 2 would be equal to 0, right? And so what then would happen is you don't need those constraints. The constraints would be inactive. lambda 1 and lambda 2 would be equal to 0. Okay, so it's a riskier approach. What if we land up with unusual solutions b equals negative something or h equals negative something? Only then we'll have to go back and include these constraints. But let's take a risk. We know that it's a practical problem. The solution would always have b and h strictly greater than 0. That's our intuition. Yeah.
So we know that this b and h should be greater than 0 practically.
Yeah.
So,
which means that the constraints would be inactive. Lambda 1 and lambda 2, right, would be inactive. They would be equal to 0.
So can we also do something like by adding some positive epsilon greater than a? Because in this way we will eliminate this active state by adding the epsilon. Like bh plus pi over 8b square plus epsilon is greater than a, where epsilon
Well,
is
you can simply use square root of b and square root of h as the variables. And so this would be, they all will be, these would be quadratic terms. Same thing, right? So, but epsilon wouldn't solve the problem. Epsilon, I explained you could use something like that when you have a strictly greater than or a strictly less than. Oh, I see. Here, yeah, you have that. Yeah, but yeah, I guess you could do that. But the simplest way is, you know that b and h will be strictly positive, and therefore just ignore those constraints because they're going to be inactive anyways. Okay, and so only look at this is the simplest possible approach. Other approaches with 5 variables, you can always take care of that. But in that case, what would happen is the problem, solving the problem would involve 5 variables instead of just 3. Okay, so, and if you get something unusual, then obviously you made some error, you'll go back to the drawing board to see what mistake you made, or what's the reason why you're getting an unacceptable answer. Okay, so let's proceed in the simplest possible manner without using your trick of using epsilon. If you use epsilon, then the solution might be b equals epsilon, right? Like an infinitesimally thin slice of bread, something like that. Okay, so this is the primal problem. This is the problem, constraint optimization problem. We'll only look at the primal and then solve it, applying the KKT conditions. This is our Lagrangian. I'm calling the Lagrangians. Okay, this alpha and beta would have corresponded to this, h and b. Okay, but from our argument, we'll just have b, h, and mu. We'll ignore the alpha, beta, which would have corresponded to h and b being greater than or equal to 0. Okay, so taking the derivative, just ignore the alpha and beta. I wrote this so that we would remember that it actually has 2 hidden constraints. Okay, so this is the derivative with respect to h. What do we have? 2 negative mu b equals 0, or mu b equals 2. Okay. Then derivative with respect to b is equal to 0. So 1 plus pi over 2 negative mu h, negative mu pi over 4b, right? So this is derivative with respect to b. And then from this, what we get? Letting mu b equals 2. Since mu b equals 2 here, you'd get pi over 2 here, right? So pi over 2 and negative pi over 2 cancel out. We get 1 minus mu h equals 0 or mu h equals 1. So mu b equals 2 and mu h equals 1. Clearly, b equals 2h. So b equals 2h. Okay, and again, we are looking at the quickest way to solve this. Friends, look at this problem now. Since we know that the ratio is b1:2, now it becomes easily solvable, right? Twice h square plus pi over 2 h square. So equals, this, we are looking at this. Twice h square plus pi over 2 h square equals a. Whence h equals this, just solve this, and b equals this. And they involve squares. We know that we have to take positive values only. This is the solution. Any questions with this? You guys have interesting questions, so go ahead. I hope I gave satisfactory answers to your questions. Your question was, why not use that epsilon, b plus epsilon greater than or equal to 0 and h plus epsilon? Yeah, we could do that, but why include 5 variables, right? Intuitively, you can discard the equality constraints altogether, and you're left with just 3 variables. It becomes a very simple problem to solve. Now, the next problem is a little more complicated. Okay, well, it's not complicated exactly. It's simple. It's a very simple quadratic problem, but you'll see how I'm using the lambdas, inequality constraint. So this constraint optimization problem involves inequalities. These are the 2 inequalities. We minimize, it's simple quadratic with 2 linear constraints, right? And so here you'll see what is happening graphically. And from the previous lecture, you know the graphical interpretation of the constraint optimum x star. Okay, in terms of the gradients would be in opposite directions, right? Okay, so this will reinforce what that graphical illustration that we did in the previous lecture. Okay, so we convert this to standard form. So we minimize, and subject to, this is G1, x1, x2. So this is our first constraint, x1 plus 4x2 negative 3 equals less than or equal to 0. And this one is x2 minus x1 is less than or equal to 0. That's G2. Okay, and these are all straight lines in 2 dimensions, x1, x2 plane. So this is the standard form of our COP. Lagrangian is this. This is the objective function, and then we must have lambda 1 and lambda 2 strictly greater than or equal to 0. Yeah?
If it's strictly less than 0, if the constraints are strictly less than...
The word strictly was a slip of the tongue. Just greater than or equal to. Lambda should be greater than or equal to 0.
No. My question is like this constraints x1 plus 4x2.
Okay.
If it's not equal to 3, but it's strictly less than 3, then still the equation would be same, Lagrangian equation.
Yeah, because we cannot handle the case of if the constraint optimization problem that's given to us involved x1 plus 4 x2 is strictly less than 3. We have to convert it to less than or equal to 3 and then solve it. And then if we get x1 plus 4 x2 equals 3, we discard that solution. Another way of doing it is if the actual problem that's given to us entailed x1 plus 4x2 is strictly less than 3. Equal to 3 is not acceptable. Okay, what did I do? I don't know what happened. Okay. Okay, so if we had such a situation, then we would know that we would write it down in this form, less than equal to 3, but we will only consider cases where the corresponding Lagrangian is equal to 0. We would always assume that this constraint, less than equal to constraint, is inactive. All possible cases where this constraint is active, we would just discard. Okay. So, and you'll get further insight into how to do that here. So this is the standard form, and this is the Lagrangian. Okay, so we have two constraints, inequality constraints, and we have two Lagrange multipliers or dual variables, lambda 1 and lambda 2. Okay, this is the case where complementary slackness condition comes in handy. In the previous example with the bread, we didn't even consider complementary slackness, right? But here we must consider complementary slackness. Okay, so here's what we have. First, we'll just take the derivative. Okay, and remember this of the Lagrangian. We'll use the gradients later. Okay, graphically, this is what we have. This is x1 and this is x2, and this is our constraint optimization problem. Let's look at it here. These contours are level sets of this objective function. Its minimum is at 0. This is the global minimum. Okay, and this green line corresponds to the first constraint. This side is infeasible for the green line, and this side is feasible. This is where G1 is, this region here is where G1 is less than 0. This brown line corresponds to the second constraint. This is where x2 minus x1 is greater than 0. This is where x2 minus x1 is less than 0. Okay, so these three quadrants here are infeasible. Okay, and we will look at, the active constraints should be tangent to the contours, right? So we know a priori that these are the infeasible cases, okay, but just ignore the infeasibility for once. This is one potential solution here. Okay, this brown line is x1 minus x2 equals 0. x1 equals x2. Or x2 minus x1 equals 0. Sorry. And this green line is x1 plus 4x2 minus 3 equals 0. Right? So here, the first constraint should be inactive. The second constraint should be active. Right? So x2 minus x1 should be equal to 0 here. And this is, so anywhere, everywhere here, but this is where it's tangent to one of these contours. So this is one potential solution. Okay.
Which one is actually the, from these constraints, which area is actually a feasible region?
Only the one that's not shaded, this.
This one?
Yeah.
So how that?
It's not. Okay, but these are potential solutions we'll be looking at. We'll see how to discard them. Now, we're looking at this graphically because it's simply in 2 dimensions, but for a larger, if we had x3 or x4, then we wouldn't be able to look at it graphically, right? So we would have to only use algebra. In that case, how to do it? Okay, so But so that we understand what's going on graphically, that's why I'm parallel processing. I'm looking at the algebraic method to do it, and graphically what's happening. So this is one potential solution. This is where the first constraint is inactive, second constraint is active. Now, this is the intersection of both these straight lines. So both constraints are active here. Okay, and here the first constraint is active. So this is equal to 0. x1 plus 4x2 minus 3 is equal to 0, but x2 minus x1 is less than 0. Okay, so this, and this are the 4 cases that we have to look for algebraically. Okay, this is when both constraints are inactive. There's no tangency involved here. This is where the first constraint is active. Only one constraint active, right? The first constraint active. This is where the second constraint is active. This corresponds to where both constraints are active. Okay, so these are the 4 possible cases we'll examine. This, we will see algebraically that this is infeasible. So that leaves us, and this is infeasible. This is also the global optimum because both constraints are inactive. And we'll see how algebraically we can discard these two. So we have this and this. This is also valid, this is also valid. Okay, and then what we will do is we'll compare which one gives us a lower value. It's this one. And you can look at it graphically, look at which contour intersects. Okay, so this, although it's valid, we'll discard this because we're trying to minimize. And so this is our solution. Okay, so now, and this is the global minimum. Okay, so this is the Lagrangian, primal feasibility, dual feasibility, complementary slackness conditions, which we shall explicitly use, and now we have 2 inequality constraints. So 4 cases. Okay, so this is the first case, lambda 1 equals 0, lambda 2 equals 0. Both constraints inactive. Which point does this correspond to? Here? This one, right? Second case is when lambda 1 is greater than 0. Lambda 2 is equal to 0, so only the second constraint is inactive. So where is the second constraint inactive? Here. Second constraint is inactive here. Right? What's that? First constraint active. Second constraint inactive. Here, it's the other point. This is where first constraint is inactive. Second constraint is active. Okay. So 2 and 3 are only one constraint being active. That corresponds to this point here. Here, only one is active, the other is inactive. This is where both constraints are inactive, and this is the case where both constraints are active. Okay, here both constraints are active.
This is the first one, isn't it?
No, first is both constraints are inactive.
Okay.
That's the global minimum.
Yes, okay, got it.
This is where both constraints are active.
Yeah, got it.
Okay, now stationary conditions. What do we have? 4 variables. Okay. Now, from the stationary conditions, just differentiate this with respect to x1, x2, and we get a set of 2 equations. Okay, we have 2 equations here which we can solve. Unfortunately, we have 4 variables. Okay, we cannot easily use these primal feasibility because it's less than equal to, right? We cannot use the dual feasibility directly. How do we harness complementary slackness? Okay, because if we let both lambda 1, lambda 2 equal 0, oh, wonderful, we only have x1 and x2 to solve for, right? Now, let's look at the other extreme. Okay, lambda 1, both lambda 1 and lambda 2 are greater than 0. We don't know their values. Here we know the values of lambda 1 and lambda 2. Well, they're 0, right? So we just solve for x1 and x2, letting lambda 1 and lambda 2 equal 0 in case 1. In case 4, we actually have 4 variables to solve. So where do we get 2 more equations? Now, since lambda 1 and lambda 2 are greater than 0, it means that, well, x1 plus 4x2 minus 3 must be equal to 0. So this equal to 0 will give us another equation. And similarly, lambda 2 greater than 0, fine. So x2 minus x1 must be equal to 0. The constraint is active, right? Okay, so here, like we're looking at this case, both the constraints are active. So this is another equation we can use. This is another equation we can use. Okay, so in that case, we would have 1, 2, and 3, and 4 equations. 4 variables and 4 equations. Again, solvable. Now, these 2 cases, in each case, I'll just examine one case. Here we have lambda 1 is greater than 0. Right? Lambda 2 equals 0. So actually, we have, just ignore lambda 2 here, it's equal to 0. We have 3 variables, x1, x2, and lambda 1 to solve here. But since lambda 1 is greater than 0, we also have a third equation here, x1 plus 4x2 negative 3 equals 0. Correct? And so let's look at, you can easily see how to attack this third case. So we will now look at all 4 cases. Again, this is what we have. Okay, these are the 4 cases. So I write down all the KKT conditions. Case 1, lambda 1 and lambda 2 are both equal to 0. Okay, so from the station, no active constraint. So it's actually the global minimum, right? So from the stationary conditions, we have x1 equals 2, x2 equals 1. Solve this. Lambda 1 and lambda 2 are both zeros. So x1 equals 2 and x2 equals 1. Correct? To make both sides, right-hand side, 0 in both cases. Now, why do we discard it? Because once we're looking at 4 cases, in all 4 cases we'll solve it and we'll check if all the KKT conditions are satisfied. So let's look at if this constraint is satisfied. We must, if you G1 is this, it's greater than 0. So it's not satisfied, right? It must be less than equal to 0. So G1 is greater than 0, which means that the first constraint is being violated, and graphically, we are looking at this case. The first constraint is being violated here, right? This green is the first constraint. It's also violating the second constraint. It's violating both the is it violating? No, it's not violating the second constraint. Sorry. It's only violating the first constraint, G1. Hence, we reject that solution. Okay, primal feasibility is violated. So case 1 over, we reject the solution. Case 2, x2, well, now what we have, this is again still case 1, we just rejected. This is the global minimum and we rejected it. Now we look at case 2. Here, lambda 1 is greater than 0, right? If lambda 1 is greater than 0, then we have 3 variables. What are the 3 equations we'll use? First, these 2 equations. Lambda 2 is still equal to 0. The first constraint is active. Okay, the first constraint active implies this must be equal to 0. So now, from the stationary conditions, replacing lambda 2 with 0, we have this and this. Now we again have 3 equations to solve. Okay, here, so the solution is this. 1.667, 0.333, 0.667, and lambda 2 is 0. We assumed in the beginning that this is an inactive constraint. Lambda 2. Where's my cursor? Ah. Somehow the cursor, okay. Okay, so this is my solution. And we have to check, well, that this is, G1 is equal to 0, just like our assumption, right? This must be equal to 0, satisfied, right? And G2 is x2 minus x1 should be less than 0. X2 minus x1 is always negative 1 in this case. So this condition is also satisfied. So we'll retain. And what are the values of lambda 1 and lambda 2? Lambda 1 is 2/3, so it's greater than equal to 0. So the primal and dual feasibility constraints are being satisfied. So this is a potential solution, valid solution. Okay, we'll retain it, this one. And which was this corresponding to? This point. The first constraint was active. Lambda 1 is positive. Lambda 2 is 0. Second constraint is inactive. Case 3. Lambda 1 equals 0 now, and lambda 2 is greater than 0. So, well, we have this here. Lambda 2 is greater than 0. So we have x2 minus x1 equals 0 as one equation to use. And we also have x1 plus 4x2 minus 3 should be less than 0. G2 is active, right? So x1 minus x2 equals 0. And from stationarity, we get these two. We have to solve for x1, x2, and lambda 2 because we know lambda 1 is 0. Solving, we get these as the values. Is this good?
No.
Why?
Lambda 2 is negative.
Exactly. Okay, lambda 2 is negative. So, lambda 2 is less than 0. Dual feasibility is violated. We discard it. Okay, so this is the case. x1 equals, this is 1 point, so it's this case here. Okay, we have to reject it. Now, this is rejected, right? So now, and you can see why it's rejected. Graphically, lambda 2 is less than 0. It means that the gradients of f and G2, they should be in opposite directions, right? But they are in the same direction. You can manually compute it and see. Okay, now we'll look at case 4. Case 4, and then that gradient thing I'll show you in case 4. So here we have lambda 1 and lambda 2 both strictly greater than 0. So we have two variables, two extra variables. So in all we have 4 variables to solve. Okay, so G1 and G2 are active, which means that this is equal to 0 and x2 minus x1 is equal to 0. Okay, so 2 equalities we have, and we get the other 2 equalities from the stationary conditions. 4 variables and 4 equalities. So this is the solution that we get. I'm sorry I couldn't get I had to express them in terms of decimals. Okay, so this is where we land up with. Is this valid?
No.
Yes. Why is this not valid? Lambda 2. Okay. Now, on the face of it, why it looks like it's valid,
Yes.
right? Why is it invalid? Okay.